So for the folks in Zoom, do you get an audio output when I play this? If you can just let me know in chat, would be super helpful. Okay, great. Thank you. I'm not 100% sure if all the audio files will work. Oh, we don't want that. But in case the audio files don't work, the notebook, if you run the notebook, you'll be able to generate your own audio files or download them. Okay, so with the audio test out of the way, let me get started. Okay, so we'll be continuing our discussion of natural language processing with a little discussion on the phonetics and speech technology side. So as you may know, as far as communication is concerned, when we utilize a written form of communication, we're able to directly look at lexemes and morphemes and syntax and parts of speech and sentence. But when we have a speech signal, when we are talking to each other, this adds an additional layer of encoding and decoding, which has to be done to the speech signal so that we can extract linguistic information from it. And this is where speech technology comes in. I have a lot of demonstrations as well as content today. I can't promise that all of it will work because Google Colab does not like a lot of heavy things to be run. But I'm going to try my best to get through everything. And in case I encounter a bug, I'm going to try my best to fix it. All right. So as far as speech technology is concerned, the parts that we are interested in is the processes and pipelines that we are going to be using to, in part, record or generate, encode, process, and decode human spoken language. Our purpose for speech technology could be voice recognition, transcription, biometrics, so voice, in case we high level voice recognition, as well as speech synthesis and machine translation with a speech component. So for the Star Trek fans out there, the universal translator that each person has embedded in their brain, many parts of that universal translator would need speech processing in order to work. In association with or along with the natural language processes that we have looked at previously, human language can be processed at multiple linguistic levels. So we can extract phones and the sound patterns from the raw signal, locate different parts of speech from it, process it, as well as output it in a mirror pipeline. As far as the advancements in voice capturing interfaces is concerned, we've been able to run bigger models. We have better GPUs, we have more storage capacity and deep learning. And so with all of these advances, speech technology has also come a long way where we're able to process human conversations in almost real time. We're able to generate voices that are very natural sounding. And this is something that has added to accessibility and a more natural interfacing with machines. Some of the popular use cases for speech technology or voice technology are speaker diarization and biometrics. So if you have a file which has lots of speakers, something that we might be interested in is to know which sentence or which utterance or which turn was taken by which speaker. And that's where diarization comes in. It's something that we can do automatically with high accuracy. Biometrics, so if we are able to perform voice recognition, there's a great deal that we can achieve as each of us has certain voice characteristics that make us different from all other speakers of a given language. Next, we can do transcription as well as captioning and voice typing. So if we have a language model attached to our speech processing system, we can use it to turn a raw speech signal into text. We can use predictive text generation along with it. And because the lag time nowadays is so low, those of you who have, if I was to, for example, enable captions in our Zoom chat today, uh, you would see how efficiently we are able to use captioning in order to work. Next is sound source identification. If we have a sound file where there are different there are different sources for the sound, we might be interested in knowing what all we're hearing. Are we hearing a car? Are we hearing a guitar? Are we hearing bird sounds? Are we hearing people speaking? So sound source and identification is also a great use case if we are able to process sound. Speech synthesis. uh, Speech to text is text to speech is a great use case for us inputting text into a prompt and having a natural voice with maybe different accents or different voice qualities speaking back to us, speaking our text back to us in speech. Then this is something that lends itself to the voice assistants and other voice activated technology, where we want to make sure that activation commands and specific prompts are properly understood so that our assistants do what they have been requested to do. Now, a lot of our communication is not just words, but also emotion and sentiment, and a lot of this tends to live in the speech domain more than just the text itself. So if we are able to run multimodal models where the speech signal can be utilized, this improves our emotion, sentiment analysis work, as well as voice recognition work. Finally, we've got machine translation and language detection. Again, if we are speaking to each other and we are using speech, a great thing to do would be to understand the unique characteristics, linguistic characteristics of different languages, and use this to improve translation from one language to another using just speech. And with speech, different languages have different sound patterns and systems and prosody. So we want a robust model that's able to utilize all of this information while recognizing the language being spoken, understanding what the output language is, and working with both of these systems together. So this is just a little image from an NVIDIA lecture where they talk about all of the elements. The little panel on top is the ASR panel, where we have the different steps for automatic speech recognition. Once because the natural because speech technology may involve search, semantic search, or information extraction, we want a natural language understanding system that is able to perform our search and get rid of any typos or misspoken elements, and use a language model as well as a search system in order to get us what we need. Maybe translate it into another language if needed. And once we have this text output or the machine interpretable output from our natural language understanding system, we might want to turn it into a speech signal in order to be outputted. And that's where the text encoding and the speech generation system comes in, which is at the bottom panel. So even though when we maybe give a command to Siri or Alexa, the amount of time this takes is mere seconds. The number of pipelines that our information has to pass through, and the number of times it has to be transformed is pretty overwhelming. And as with any complex system, we have a lot of terminology and we have a lot of jargon. And I'm going to try, at least with today, to maybe give an overview of some of the terms that might be important to bear in mind when you are engaging with a system, an ASR system, whether you're building it or using it, just so that you can optimize your usage. Let me start with some terminology. I've used the term automatic speech recognition, or ASR. This is something which involves converting spoken language into text. This is done by recognizing the speech patterns and language-specific information. Next, it is interpreted into it's interpreted into written language, and this written language, or the tokens generated from it, are then passed on to other pipeline systems in order to be processed. And this is something that we would use as far as virtual assistants are concerned, where they're trying to listen to a lot of audio and picking out specific user commands so that they know what to do. So if you want to ask your system to make an event in the calendar, not all words are going to be useful. Not all parts of the signal are going to tell the assistant what to do. So it needs to be trained to understand and look for words like calendar or event. And that's where ASR comes in. Next, we have natural language processing, and this is the understanding, interpreting, and generation of human language component. We've talked about it a great deal in our workshop series, and I invite you to check out our previous sessions in order to familiarize yourself more with NLP concepts. Next, we have speech synthesis, where we're using an artificial production system in order to generate a facsimile of human speech. And in this case, it could be, our prompts could be in the form of a spoken word that's getting interpreted by the machine, or it could simply be a text prompt where we're giving it a sentence and asking and some parameters and expecting a speech signal as the output. Then we've got text to speech, where our input is text, and the text is being outputted as spoken words. The voice user interface is any system that is acting as an interface to allow users to input their voice commands and pass this input on to further parts of the pipeline. Then we have an acoustic model, where it's usually, like, I'm being very general here. It's usually a deep learning neural network model or probabilistic model, and it's the training for this model is to help it to represent the relationship between different linguistic units of speech and the audio signals that they could actually expect in real time. So, for example, the vowel ah, there is a little unit, a little phoneme that we might be saving that represents that sound. And we've got maybe millions of speakers who might utter the sound ah in different ways. And we need an acoustic model that can basically listen to different renditions of the sound ah and come to a conclusion that they're all the same phoneme, right? Then we have a language model, which is the linguistic side of our processing, where it's taking all of the output of our acoustic model, and it's trying to assess what kind of words, what kind of parts of speech, what kind of sentences can potentially exist if a given set of sounds are given to it, right? And we have got something else. We've got a few other words that you might encounter, like wake word. So in the context of an assistant, it might be something that our model wants to really pay attention to in order to start all of its processes and otherwise remain dormant. Okay. So very briefly, speech technology has been in the process of work for quite a few decades, and we went from originally building actual big systems with little voice boxes and sound storage systems that could be used to combine little sounds together with buttons in order to generate speech. And that's something that was created with the acoustic mechanical speech machine. And there are many names, terms, and varieties of these speech machines. There are some very, very cool systems that use softer mediums that resemble human musculature and tissues to generate more natural sounding sounds. So we originally, as far as speech production or artificial speech production was concerned, we were definitely looking at artificial machines that could produce sound. At the same time, there was also the speech recognition or word recognition problem. Originally, we started by a model that could only recognize sounds produced by one given speaker. And as time went by, our models were able to work more to understand more words, and more importantly, recognize the same word when it is generated by different speakers. So whether it's a baby or a human male or a human female, we want our model to be agnostic to those characteristics. With the advent of or with the research around hidden Markov models, we got really good at predicting upcoming phonemes. So if a given phoneme is a P, what is the likelihood or what that the next sound is going to be an E or a A? And so we were able to use these predictions in order to process sound in a much faster way, right? And at this point, our technology became more usable, and so we had speech recognition that was used for commercial as well as government processes, which are kind of hinted at these last couple of slides. So this is a briefest possible history of speech technology. I would love to delve into more detail. It's amazing, and there are some resources that I could point you to if you're interested in learning how we got here. Right now, at this point, I think we have enough to go on to the demonstrations. But in case, I'd like to add a little bit more about the linguistics side of speech technology and what is the information that phoneticians, physicists, as well as other scientists were using in order to understand automatic speech recognition better, right? So this is extremely short, and there's a lot I can say, but I'm going to try to be as concise as possible. Right. So first up, we might need to talk about the propagation of sound itself. Sound propagation usually requires a sound source. So we need something that's vibrating and producing longitudinal waves. The longitudinal waves that are being produced will have compressions and rarefactions. They need a medium in order to propagate. So we won't have sound propagating through vacuum, but it's going to propagate through helium or the natural atmosphere. And finally, we need a resonance tube in order to dampen certain frequencies and amplify certain frequencies, so that the same source can produce a variety of different complex sounds that we can use to actually encode information. So if it is of interest, there's a great primer on what longitudinal waves are and why we would be interested in them. It's right here. There are some great tutorials over here that I recommend. Then we've got a few phonetics / physics concepts that we might need when we're looking at any kind of speech or sound related research. We might need to know how much energy is there in the systems in our signal. So that's looked at with amplitude. We might need to know how long the wave propagations happened. We might want to know if a complex wave has many different components, we might want to know what the frequency is or how often each of these waves are oscillating per unit time. And we have simple and complex waves. With regard to human speech, it is a complex wave. It's got lots of little components that get generated at the same time and propagated at the same time. And one of the things that we're great at doing when we're decoding this signal is understanding the different components and processing them. In order to represent sound, you might come across waveforms where it's just a simple plot of amplitude of sound over time. You might see the same signal in the frequency domain, and that's referred to as a spectrum. And if you're listening to a long audio file, you might come across a spectrogram where you're seeing the changes in the frequency components of the sound over time. And these are just, if you come across waveform or spectrogram, these are just ways in which we're representing and looking or visualizing our wave. Then you might come across the term Fourier transform. It's a mathematical function that helps us represent a wave in the frequency domain. And finally, with regard to human speech, as far as we might come across the term formants, which are the output of a sound being passed through a resonance chamber. And so in case of human speech, we are producing it in our vocal folds. It's passing through our oral cavity, where we're manipulating our tongue shapes in all kinds of interesting ways to generate different sounds. In my case, if I use the sounds ah and e, they're both being produced by the same vocal folds. However, they sound really different because I have different tongue shapes for each of these. And all of this is something that we have to train a model to, at the back end, know and recognize and differentiate between. And so you might come across the term formants in the context of human speech. Then when we are extracting our acoustic features in order to perform any speech technology task, you might come across the term MFCCs. It's just another representation of sound in the power spectrum. We're capturing like little photos of our sound every couple of seconds. This could be a 5 millisecond interval or a 20 millisecond interval. And as we collect these features over time, we're trying, our aim with MFCCs is to find a vector representation of the sound that's very similar to how the human ear processes the sound, right? So if you come across any of these terms, they're just different ways in which we are interacting with sound as a medium. And I have just a few plots here. So if for a simple sound that's just a tone, we're seeing that the compressions and rarefactions are very regular. And so on the frequency spectrum, we're seeing a little dot on the 1000 hertz mark. Right, and if you want to look at a spectrogram for the 1.6 seconds or 2 seconds that this sound was played, we see that the energy is the spectrogram will just give us a sense of where the energy is in the sound. And in this case, since it's just a little, it's a very short sound, we see that most of the spectrogram is kind of it looks very, we don't see a lot of changes on it, and that would be the reason. Similarly, just a little demonstration, just a little plotting to understand formants a little better. So here I've produced a little vowel-like sound. It's got two components. So it's got a let's see here, 200 hertz component as well as a 300 hertz component. So on the spectrum, we see two little peaks. And if you look at noise, we're not getting such clean lines. And so that would be one way in which a system tells the difference between a vowel and noise, right? Because both of them, when they are plotted, they have completely different plots, right? And if I was to call the MFCCs, again, the MFCC coefficients over here are going to look very different. And if we are able to train an acoustic model to understand that different types of sounds have different kinds of coefficients, they have different, their spectrograms are going to be different, their waveforms are going to be different. This is how we would be able to essentially build a complex system that can differentiate between all sounds possible. Right. And I have a few other optional things that you might come across with speech technologies. There will be a lot of talk of phonology, vocabularies, and phones. based on the language that we are using for our processes. Each language has its own set of permissible sounds, permissible sound combinations, and when we are engaging with an ASR system, we want to make sure that it has a phonology, it has an understanding of what sounds are allowed next to which sounds, so that we can do better at speech recognition for across different languages. So in case if you're interested in testing this, try changing the language on the captions for Zoom here from English to, say, another language, and you'll see that the captions that are getting generated will seem like will not make any sense at all, because speech models need to be primed to understand which language they're going to expect. And for that, we might feed them a phonology, and we might give them some information on the phonotactics, right? Now, as far as the speech, human speech is concerned, there are certain constraints in which it operates, and these constraints are important because these make things very predictable, right? So the first thing is that we have the ability to generate a lot of sounds. And here I have I have the International Phonetic Alphabet, and almost every symbol over here is a type of phoneme that humans are capable of producing with our system. But each language will subselect only some phonemes from all of these. Secondly, there is going to be a limit on which set of sounds we can produce that will be different from all other sounds in a language. So if we have two vowels and they sound too similar to each other, we're not going to be able to differentiate between words. And this is something that we want our model to be primed for. Next, for speech to actually be useful, we have to arrange the sounds in a way that they can be differentiated. So we don't want to put two sounds that are too similar to each other next to each other, because then we won't be able to extract phonemes out of them. And this is all things that happen through the evolutionary course of a language. And it's great if we are able to give a model all of this information. Next is the NLP part. Human language is, for the most part, it's purpose driven. It tends to work across linguistic levels. So unless you're really angry and you stubbed your toe and you're just you yell out something, if you're trying to convey information to another person, you are activating your lexical level, you're activating your syntactic level, you're activating your cognitive level. And so when we are performing ASR, we want to make sure that our system is not just processing sound, but is processing language, right? And in case you're interested in human articulation and acoustic and the perception system, there's a really good demo. I'm not going to click on it because the audio can be really annoying to some folks. But if you click on the pink trombone demo, it's going to take you to a web page that produces that has a little vocal fold that's constantly moving, and you can play around with different tongue shapes to see how to actually see the physical difference between an ah and a oo. Right, and so we've got the source, we've got oral and nasal cavities which are producing resonance, and we've got different articulators that are turning our oral cavity into different shapes. And all of this produces all the interesting complex sounds that we are so used to with human speech. On the acoustic side, we are decoding or all of this audio that's coming out of someone's mouth and transmitting through air. This is done with the ear and the ear membrane, and there's a very specialized way in which this happens. And so when we are conducting speech processing, we want to make sure that this information, the way ears process information, is how our automatic system also understands the speech. Finally, we've got perception. I have a little demo over here that I invite you to click on. Essentially, when we are processing sound, it's not just the audio information that we're processing. Often we rely on visual cues, so we are seeing speech as much as listening to it. And this is a little video where the word bill is constantly repeated, but every time the image on the frame changes, you will perceive the same sound differently. So it might sound like a pail, or it might sound like the word mayo or the word bill, depending on what we're seeing. And so with automatic speech recognition, sometimes we have to operate with the constraints that it's not just the audio information, but there might be a few other sources for the information. There's also a few, like, just not to go too heavy on the terminology, but there are a few things that I thought might be interesting for those of you who are looking at speech technology in a little bit more depth. As far as encoding and storing, transmitting, and machine readability of sound is concerned, we need to process the signal with a lot of things, and this is where you might come across the terms digitization, sampling, quantization. If you're looking at the code that I have provided so far, there's a sampling rate that you might often need to provide in order to make the files work. And all of that information is also worth keeping in mind. But in the interest of time, I'll not go into it today. And if you are processing files themselves, the different formats and encoding methodology can impact whether your ASR system is capable of reading it or not. So if you have an MP3 file, you might not be able to pass it to an ASR system. You might need to convert it to a different format or a different encoding. And there are a lot of great command line tools. One of them is FFmpeg, which can allow you to basically convert a file into a format that can be readable to your system. And a lot of pre-trained models and a lot of toolkits will do this automatically for you. So, but in case you have a sound file in a very strange format, something that you might want to consider is converting it to a file system that your system can process, making sure that its sampling rate is okay, and you might need to convert your sound from your file from stereo to mono. So all of these are just other terms that you might come across, but all of this can be done very easily automatically. So all you need is the right toolkit for it. Now, I have a few demos over here for the processes that we can have as far as ASR is concerned. Just before I progress, I'd like you to just take a couple of seconds to think about all of the speech recognition, speech technology systems that you came across in the last 48 hours. Some of you could be engaging with a system, a speech recognition or speech processing system as we speak. And if there are any that come to mind, I invite you to unmute and call out your response, or put it in chat. I'd be very interested to see what you came across. Okay. In case you haven't come across any today, fascinating, like something that you can come across right now is the captioning system that Zoom generates for us. It generates an entire transcript file that it cleanly stores in a .txt file. If you've never saved the captions, that might be something worth trying out right now. And with that, I'll move to our demo section. In case the code doesn't work, I'll try to debug it in real time. The first toolkit that I want to talk about today is Koki, which is a system that offers both an API as well as a lot of great pre-trained language models. Primarily, you can use it to both call existing language models that you're interested in working with or call their own language models. And it's got both a text-to-speech as well as a speech-to-text option. So let me try this out. It's like... Right. So if I, the first thing that I might need to do is load Koki as well as get a model. So for today's demonstration, using a previous workshop session, I'm going to utilize a multilingual model that I can play with. And the first thing that I might want to do is generate a sound. So I want to generate the sentence. This is voice cloning. And in order to do this, see here. In order to do this, I'm calling a sample speaker voice that's stored as a sample.m4a. I'm giving it a prompt, which is the voice, which is this is voice cloning, and the hope is that the model will use this sample sound
voice cloning
and generate this sentence for me. And I'm not sure if all of you can hear, but let me try again.
This is voice cloning.
So it was able to use the male voice that I gave it and generate the sentence voice cloning. And in case and if you give it a sentence prompt, it's able to generate a pretty natural sounding sentence, right? So another popular toolkit for models is Tachytron 2, and it's
Soy una lingüista apasionada. Me encanta la fonética.
Right, so this is the Spanish model from Tachytron 2, and I gave it the sentence that I'm a passionate linguist and I love phonetics, and it produced a pretty natural sounding sentence for me in Spanish, right? So again, as far as speech synthesis is concerned, we have the ability to synthesize speech in a lot of languages. Koki and Tachytron 2 are some options. There's also Whisper, which I'll talk about a little bit next week. And so next, another task that might be interest to us is noise reduction. So if you provide a system with a sound file that has a great deal of background noise, how do we extract the human speech from the noise? And if you remember the little formant plot that I showed you before, there is a meaningful way in which noise, as far as its amplitude and its frequency plot is concerned, it's quite different from human speech. Utilizing this information, we are able to segregate noise from a signal. So in this case, let me see if the sound file plays. So in case you're not able to hear the audio, let me know. The first audio file that I played has a sentence in English, and there's a lot of background noise that is almost louder than the speech itself. And if I use the speech brain AI toolkit, I'm able to call its a pre-trained noise reduction model. And when I run the same audio through it,
it is a very risky business, and that is why I buy bonds, period.
We're able to kind of extract the human speech out of it. We may not get very natural sounding results because a lot of human sounds fricatives, and there are a few other affricates and nasals. They all tend to have a little bit of a noise component. So when we extract all of it, the actual voice might sound really robotic. But if our intention is to basically process a sound file into text, we might want to make sure that our pipeline is receiving the cleanest possible sound file. And noise reduction is a great pre-processing step for the NLP side of our pipeline. Another thing that we might want to do is speech separation. So if you have a convoluted signal, you've got a signal that's got two people talking, maybe simultaneously, maybe one at a time, we might want to separate our speaker from one speaker or one sound source from another. So the speech separation pre-trained model is a good use case for ASR. So in this case, I'm just going to play the mixture first.
My father has revealed the culprit's name.
Right. So if you try to pass this wave file to your NLP model, it's not going to work because there are essentially two sound signals that are being generated at the same time. So a sound separation model is a great way to make sure that our signal is as clean as possible.
My father has revealed the culprit's name.
Right, so in the first file after separation, we're getting a female voice saying a sentence. And if I play the second sound,
The bird canoe slid on the.
right, so we've got two completely different sentences with different meanings. But when we play them together,
My
even
father
to the
has
human ear,
revealed the culprit's name. My father has.
even to the human ear, it's so difficult to understand what's being said. Right, and of course, emotion recognition. So if we are able to understand if our speaker is speaking loudly, speaking slowly, speaking with a great deal of speaking in a flat tone, or is maybe speaking in a pitch that is lower than their normal tone, all of this information can tell us about the perceived emotional state of our speaker. And so this is something that we can utilize in emotion recognition. So right, so let me just play the file that I used for this. It's I used the same file as the one in our first example. So let me go over here. So I gave it the noisy file where we've got a male voice just saying a couple of words. Right, and here's a task for you. I gave this extremely noisy noisy sound file to the emotion recognition system, and the label that it printed for this sound was the word sad. Now, since we can also save the clean wave file, I invite you to try to run the emotion recognition on all of the sound files that we generated in this notebook. If you go to your files section, you'll see a lot of sound files that got downloaded and are temporarily sitting here. You can call each of them in this line and see what the emotion recognition system thinks is their emotional state. And if not, you can also generate your own sound files and play around with a sentiment and emotion classifier, right? Finally, we might be interested in speaker verification. This is a task where we're trying to understand if two given sounds, two given sound files are being generated by the same speaker. Is the same person uttering both of them, or are they different from different speakers? And for this speaker verification task, we want to use the speaker recognition pre-trained model. Again, all of these models live on Hugging Face, and you can call them with just a simple, easy command. And the amount of time it takes to download and set up will also be available to you. And once you have your pre-trained models from a system like SpeechBrain, you can use it to process it, right? So here I have two example wave files. And what I'm trying to do is ask my system if they're from the same person or from different people.
The birch canoe slid on the smooth planks.
So in the first case, we've got a female sounding voice.
My father has revealed the culprit's name.
In the second case, we also have another person. And if you listen to both of these files very carefully, you'll notice that there's a difference in prosody. There's both of them seem to have different fundamental frequencies, like their pitch is not the same. They're not speaking at the same rate. They might be slower or faster. And all of this information can go into, can be provided or extracted from a speech recognition system or a model. And in this case, we're getting the prediction false, and and it also can output a score for you. How confident is the model in its prediction? So in today's workshop, I've covered some important key elements and terminology that you might come across if your NLP processing system is going to include speech. And there's a great deal to look at. Most of this information takes an entire semester to transmit, but I've tried to make sure that I've covered the terminology and an overview of what you might need to start with speech processing. I provided a few demos over here. Most of these are pre-trained models that you can call, even if you use a extremely buggy and slow system like Google Colab, you'll still be able to set up and run all of these demonstrations. Now, there is one important thing to keep in mind, that would be the file size. In each of these examples, I gave very, very short files, and so the processing only took a couple of seconds. If your audio file is maybe an hour long, there might be other ways in which you can pre-process it to make your pipeline run faster, but that would definitely, it'll be something that adds to your overhead. In the speech separation example, we only had two signals that were intermixed. It's possible that you might have 3 or 4. So how complex is your speech processing task is something that's going to affect the overheads. But these are some of the cool things that we can do very easily. All of these toolkits also allow for pre-training. So if you have your own task, for example, I look at phonetic accommodation, and that's not something that I have a pre-trained model for. And that's something that I have to build my own pipeline to do. All of these tasks, all of these toolkits have very easy, straightforward ways to implement a implement a pipeline for your own task and for training your own model. And there's at the bottom, I have a few just references, a few articles and books that I came across that helped me prepare for today's session. And finally, I'd just like to end with a little game. It's that a lot of that basically uses all of the concepts that we have today. So this is a Wordle style word guessing game where you have to use the little spectrogram on top to guess what the word is. We know that this word has about 5 phonemes. So in case today's session made sense to you, you might already know what a phoneme is. And finally, if you get the word right, it gives you a little audio file that is made by combining all of these phonemes, and it also gives you a transcription. So it's a very simple website that is using so many of the speech processing pipelines that we discussed today in order to create a cool and fun game. So with that, I come to an end of today's workshop. Next week, I'll be specifically focusing on transcription tasks and how to generate transcripts, what are captions, how to pre-process them so that you can pass them on to a language model, what is word error rate, and if there are any more interesting speech processing tools or demos that you might be interested in, please let me know. I'll be happy to include it. Thank you for coming today.